Soul-coded. Soul-coded.
Hey! Yeah, hope you sleep well. So first talk of today is Andy Campbell from GitHub, and he'll talk about low-level programming. So hope you all wake up now. Welcome, Andy.
It's working now? Yeah. Okay, so over the past couple of days, people have been asking me what this talk is about, basically. And I sort of have had thought in my head that I've always called it systems programming and Ruby systems programming. But that makes it sound like this is a talk about how to program a system or like all these low-level things. And it's not really so much about that. It's much more about just knowing sort of the tools that you use and the building blocks that build up the systems that you already program in, all the application code. So that said, we are talking about systems programming a little bit here. So what does that even mean? What are we talking about in systems programming? This is a definition from Wikipedia. It says to operate and control the computer hardware and to provide a platform for running application software. And I really like this definition because it kind of breaks it into two pieces. First, we're operating the computer hardware. So this is something very low level. It's interfacing with the hardware itself, the memory, the disk I/O, the monitor, the sound card, anything like that. But we're also providing a platform for running application software, which means that this is the kind of software that other software runs on top of. This is nothing that a user's ever going to see directly, which I think is kind of interesting. So we're talking about application software. This could basically be anything, right? This could be an iPhone app. This could be a game, a video game, something that runs on a set-top box. But I'm going to talk about web software because I think most of us are web programmers. I'm definitely a web programmer. I mostly write Ruby on Rails. So I'm basically going to be talking about the software stack between the kernel and the hardware all the way up to sort of the bottom of the application software that we write, so like the bottom of the Rails app. This is the stack that I'm going to talk about. We're going to start all the way at the bottom and build our way up. So we're going to start at the kernel, where we're going to talk about how that interfaces with the hardware. System calls allow you to call into the kernel. File descriptors that we use to talk about anything that looks like a file in the system. BSD sockets, how we do network programming, and then a little bit about HTTP, and then at the end we're going to talk a little bit about a full HTTP server written in Ruby. In general, this should apply to sort of any Unix system, but anything specific that I talk about is going to be geared towards Linux, because that's Linux x86. This is kind of low enough level that it actually depends on which system you're talking about, and some of the things actually depend on what architecture and hardware you're talking about. So, starting at the bottom. First we have the kernel. And the kernel's the thing that runs the lowest possible level in the system. This is going to be interfacing directly with the hardware. And kernel programming is actually quite different than systems programming. They look kind of similar. It is still providing that platform layer for other code to run on top of. But the nature of how you do that is very different. You're running inside the kernel. You're mostly writing device drivers and dealing directly with the very lowest level of hardware. The systems programming that I'm talking about is sort of one level abstracted above that. This is a very basic diagram of how a computer works. At the bottom you have the hardware. So this could be anything from the hard disk network stack, memory management, I/O of any kind, anything like that. In the middle there you have the kernel layer that's providing the interface to all that hardware. And at the top, this is where anything you think of as a program runs. So any programs on the computer, anything that's actually doing anything real, right? So your code, pretty much any code that any of us write, is going to live in that top green layer. So your code, we run this in what's called user mode on the system. And the things that you can do in user mode are really, really limited without calling into the kernel. So there's kind of two things that I think that you can do in user mode. One is what I call math. So this is anything that's modifying stuff that you already have access to. So this could be as simple as actual arithmetic, where you're like adding numbers together, modifying strings, concatenating strings, or like doing crypto crazy math, like actual math. But the idea is that you have things already and you're basically just modifying them locally. So you're running commands on the CPU. But you're not getting anything from users or sending anything out, right? And the other thing you can do is you can access memory. But this is only the memory you've already been given access to by the kernel. So you can read and write from memory and sort of keep track of stuff, but you can't allocate new memory. So what's not here? It's like everything, right? You can't listen on the network, you can't write files, you can't put things onto a display, you can't allocate new memory, you can't fork processes, you can't even exit. You can't quit your program without calling into the kernel. So the kernel, on the other hand, if you're running code in kernel mode, it can literally do anything and everything. Like there's nothing it can't do. Code here can access any memory, read and write. It can modify processes. It can talk to any device, write anywhere on the file system. It manages the file system, everything like that. So because we have these two modes, and we obviously need to do some of the things that the kernel can do, you might imagine that the way this works is that you kind of chug along in user mode, and then you need to do something that goes into kernel mode, and you switch contexts. So you need to write a file, and then you switch into kernel mode, you write a couple of lines of code that then write that file, you switch back to user mode and continue on your merry way. This is not how this works at all. Anything that runs in kernel mode, because it can access anything, you don't get to write code there. You don't get to run code there. All you can do is ask kindly for the kernel to handle things for you. And the mechanism we do that with is called system calls. So system calls are basically how everything gets done in a computer. This is how most things happen. Again, we have our diagram here with user mode and kernel mode. The hardware's down there at the bottom. And your program runs in user mode. And then through this interface that kind of allows you to access into the kernel, you can make calls into the kernel. You can see what kind of system calls your program makes with this strace command. This is on Linux. There's similar ones on Mac and BSD and things like that. You give it the process ID of the process you want to inspect, and you can see every single syscall that this makes. This is stracing one request locally on the Gist app. I work in GitHub, so this is an app that I work on. You can see that it does kind of all kinds of things here. So these are all the syscalls on the left here. There's a bunch of obscure ones that I don't really understand that well, including sigproc_mask and things like that. But there's some more sort of normal ones here too. We have close, accept, get parent process ID, send to. These are kind of familiar, maybe. I'll talk a little bit more about all of these later. So the syscalls come in much faster than the frame rate of the video. Over the course of that request, there was 120,602 calls. So you almost literally everything that we do happens via this mechanism. You don't see it because it's wrapped in these other APIs, but basically everything we do goes through the system calls, especially with web apps where we're dealing with the network and file I/O and databases and things like that. So because everything we do goes through system calls, and we know that we have 120,000 requests, or system calls that go for one request, you might imagine that this API is really, really large. And in Linux, at least, it's really small. There's only a few more than 300 system calls, period. And syscall_table.s is the actual assembly code that is in the kernel that lists all the system calls. You literally cannot have any beyond that. If it's not in that table, it doesn't know what to do with it. So how do we make system calls? I was talking a little bit before about how we switch modes and call into the kernel. This is the actual assembly. This is x86 assembly in Linux. This is for the open system call. There's a little bit of formatting there. There's supposed to be spaces after the moves. So this is the open system call where you open a file to a path and you get a file descriptor back that you can talk about. Every system call has a number associated with it. Open happens to be number 5. That's what that table shows. So you move into the EAX register number 5. You put the args and corresponding registers there and beyond. If you have more than 5 or so arguments, you have to use a different method, but that almost never happens. And then you trigger this interrupt. So this is triggering a software interrupt with the code 80 in hex. And that fires the interrupt handler in the kernel. The kernel looks up what the 80 hex syscall handler or system handler is, interrupt handler, which happens to be the syscall handler. The syscall handler looks in the EAX register, sees what number that is, looks it up in the syscall table, and then executes the code. But you can see how you're actually performing an interrupt, so your code is not running anymore at all. It's all on the kernel. You don't get to do anything here. And then eventually it'll return back to you, and you get back the results. So another kind of fun fact here, of those 326 system calls that exist in Linux, 65 of them are implemented as the sys-ini syscall, which stands for not implemented. So the way that the syscall table is built, it has to be linear, it's complete. So if we deprecate a syscall or reserve one for future use, or one's implemented on one platform but not another, you still have to fill in the blanks. So 65 of them aren't actually implemented at all. They don't exist. There's only like 260 left. So Linux is actually really small with its syscall table. Other operating systems are much, much larger. Windows, we don't have this file, so we can't grep for it and see how many there are, but it's widely rumored or assumed that there's many thousands of them. I find it really interesting that basically with 260 syscalls, we have as much power in the Unix world as you have to have thousands to do in Windows. Kind of like the smaller API. So I'm going to talk a little bit about file descriptors next. All of those syscalls, or many of those syscalls, deal with reading to, writing from files, and things that look like files. And in Unix, they go by this philosophy where they call everything as a file. This is not quite true. Some operating systems take this much, much further than Linux does, or Unix does. But most things are treated as files, anything you're going to read and write to. This is a list of things that are files, not exhaustive. You can see a bunch more. So obviously files are, but also things like directories, hard drives, symlinks, sockets, any sort of, almost any device, printers, graphics cards. I don't know if you've played with the one in the lobby, that would be the kind of thing you would write to as a file. Terminals, Unix sockets, pretty much anything. And the sockets one there, we'll talk about that a little bit more in a moment. So once you have one of these files, there's a handful of syscalls that all work against those files, and they operate with file descriptors. So this is the pretty much the entirety of the file API, things that you can do with file descriptors across all of the kinds. The first three are common to everything, anything you can read to and write from, or read from and write to, and close. So this could be as simple as a file, writing to the file. Could be a network socket where you're reading off the network socket. Could be a pipe, doing IPC, inter-process communication, anything like that. You can close the files. lseek is kind of a special one. So lseek is where if you're reading from like a normal file, you can like go to the end or the beginning or something like that. But if you're reading from a stream, you obviously can't do that. So the API still works. You can call it against a file descriptor that points to a stream, but it'll return an error. So it's kind of a special case there. And many of the files that we talk about actually are implemented as streams. So this is a unicorn process on production at GitHub. These are all the file descriptors it has open. So there's a couple of interesting things here. One of which is that, I don't know if you guys are familiar with the proc file system, but in the everything is a file case, one of the things that's a file is information about processes on the system. So we're looking at the directory that's proc/process_id/fd. That's the list of all the file descriptors that are open on Linux for a process. And you can see we have a bunch of file descriptors open. There's a couple of things to note here. One thing is that the first three, 0, 1, and 2, are special file descriptors, and pretty much every process has them by default. You can close them if you want to, this one didn't. They are 0 is standard in, 1 is standard out, and 2 is standard error. So this is normally like what you would read to and write from when you're like typing into a console. This is a unicorn, so we have closed the standard in. We're not reading from def null because there's no input, and we redirect both standard out and standard error to this unicorn log, so that way we can cat it later and look at it. There's a couple other logs that are open there. There's the production log in file descriptor number 10. There's a pigments log for when we do syntax highlighting in number 35 there. But pretty much most other things, there's a couple of pipes, but most other things are these sockets. And sockets are how we do network communication in Unix land, and actually most other places as well. So one of those sockets is probably the listening socket, the one that we're listening for incoming connections on, because we're writing a web server here. Some of them are probably like a MySQL connection to the MySQL server, Redis, Memcache, things like that. One of them might be an established connection for a client we're actually processing right now. So these could be sort of any kind of network connections, and they all look like sockets. But what's cool is that they also are all file descriptors. So the way that we handle them once they're created and once we're dealing with them, they look exactly like files, look basically like files. So the file API on a couple of slides ago, we just had the read, write, and close things. We don't have a way to open new file descriptors. And that's because each different kind of file descriptor that we talk about has a slightly different API for creating one. Once you have one, the API is consistent. But if you're opening a file versus a socket, you have a different API. So the API for dealing with sockets is called the BSD sockets interface, or BSD sockets API. First, a little bit of history here. I think this is really cool. I don't know if anyone else does, but this is kind of a little history of Unix for the past 40 or 50 years. So in the early 1960s, like I think it was 1963 or 1964, there was a project called Multics that was started at MIT and Bell Labs and a few other institutions around the country, mostly in the US. And they were trying to create this new operating system. This is when operating systems weren't really a thing. So if you were writing code, you had to write assembly that handled all of the hardware yourself. There was no API to it. So they were trying to make this multi-user operating system. They called it Multics. It was a research operating system, and it was never successful. It never worked very well. It was really complex, and it never succeeded at all, really. No one ever has used it as an actual operating system. But out of that, Ken Thompson and Dennis Ritchie in 1970 kind of threw all that code away, had a much smaller team, still at Bell Labs, and they decided to scope the project down a lot and try and make a really simple operating system that was much more extensible and much more flexible over time. And they created Unix. And that's kind of the history behind the name as well. I don't know if you knew this, but Multics was intended to be multi-user. Unix, as part of the downscoping, was single user. So Multics, Unix. They dropped the CS and switched to an X at some point. So at this time, AT&T Bell Labs was part of the antitrust settlement when they got rid of all the Bell Labs things and split into the baby bells and things like that. And one of the things that they couldn't do as part of the antitrust settlement was license the operating system without giving away the source code. They were prohibited from basically keeping the source code to themselves. So they had to license it to other institutions, other universities, and things like that, including a bunch of research universities. So a few years later, 1978, a man named Bill Joy created BSD with a team at the University of California, Berkeley. And this was taking the same version of Unix that was originally written and porting it to VAX, and also adding a bunch of software around it. So that was sort of like a more complete thing. This is where we now have like Linux distributions. This was basically the first sort of distribution of Unix, called the Berkeley Software Distribution. Bill Joy is also one of the things that he added to Unix at this time was a text editor called VI, he's somewhat famous for. So after BSD 1 came out, a few years later, 5 years later, 1983, BSD 4.2 came out, and this was right around the time that the standards for TCP/IP were getting finalized, and the first TCP/IP stack was implemented in BSD 4.2. And the API that they came up with was the sockets API that, to this day, is still the API that we use. And in fact, this is one of the few things that was taken from Unix and ported to Windows. So the Windows API for doing network programming is also largely based on the socket API, which just turned 30, it turns out. So I just think it's really cool that we're writing code today that still uses this same exact API from 30 years ago, built on top of software that was written 40 years ago, with roots almost 50 years ago. It's kind of cool. So this is the BSD sockets API. This is about probably half of it or so. This is the server side. If you're making a client connection, you would use a slightly different API, but I'm going to go through each of these in turn. It's really simple. The first one there is the socket syscall. This creates a new socket in the system. This is where you tell it what kind of socket you're going to do. So this could be, most commonly, it will be TCP, so you're going to TCP/IP, so IPv4, TCP connections. It could be UDP rather than TCP. You could do IPv6. You could use Unix domain sockets, and then they get really esoteric really fast. But probably in our world, it'll be TCP/IP. The bind syscall takes that socket and binds it to a port and an address in the kernel. So this is where the kernel associates with which incoming socket or what incoming port goes to which socket that you're listening on. Even after you bind it, you're not ready for incoming connections. You have to make the listen syscall, which turns that socket into a passive mode listening socket where it can accept incoming connections. Then you can accept connections from the socket. So once it's listening, new connections can come in, and then you can call accept. That'll take one of those connections off of the socket, create a new client connection for you, which you can then read from and write to talk over that socket. The last three there should look pretty familiar. That's just the file API. So once you've accepted that socket, the client connection you have is actually a file descriptor, and you can read from it, write to it, and close it just like it looks like a file. So this API doesn't care what data you send across the wire, and you can send whatever you want, but we kind of need to agree on what we're going to send over the wire. So we need one more level up for how we actually communicate across this system. So the one we would use, this is where it gets into more web programming. We're going to talk a little bit about HTTP. HTTP, you probably all know this is pretty basic, but it's always, pretty much always request response. So you create a new connection, you ask for a request from the server processes the request, sends a response back, the connection is closed. That's the simplest version. HTTP can handle other versions as well, but that's sort of the simplest. So this is a sample HTTP request. The first line there is kind of the most important. That's where you're going to have the HTTP verb, the path, and the version of HTTP you're going to be using. That's across every HTTP request that you get. Beyond that, you just have a list of headers. So this is a curl I did against Google, accepting any content type. If this was a post, there would be a blank line, and then all the post content, maybe like the form contents or some JSON or something like that. The server then processes the request and responds with a response. Very similar response style. Again, the first line is consistent across all HTTP. You have the response version, the HTTP version, and then the response code. And you always have both the number and the text string, so this is 200 OK. This could also be 404 not found or 500 internal server or whatever the response code is. Again, a list of headers coming back from the server, and then a blank line in the content. So this would probably be HTML because the content type's text HTML, but could be anything else. That could be application JSON or whatever. So on to code. We'll have some code. So some caveats before I show the code. This is a really tiny actual HTTP web server. It's not production at all. It has huge security holes and should never be used for anything real, but there it is. I'm going to go through this line by line, but this is 23 lines. This will run. I'll show it running in a second. So first, we require the socket library. This is how in Ruby we set the socket library up to be used. We define some constants to be used later. This is the HTTP codes. Then we get into the meat of it. So this is the socket API call. So this is calling down into the socket syscall, creating a new socket with, this is a TCP IPv4 TCP connection. If you were doing UDP rather than TCP, that would be datagram rather than stream. You could do INET 6. And again, you get down into esoterica really fast, but this is the most common. This is the bind syscall. So we create this structure that represents the 127001, so localhost on port 11080. And then we bind that to the socket. So now the kernel is listening on that socket. Well, it's not listening yet, but that socket is associated with that port down in the kernel. We call listen on that socket to put that socket into passive mode where it can accept incoming connections. The parameter there, 5, is how deep the queue is. So while you're processing one connection, another connection can come in that you'll accept on the next round. And this basically says that 5 connections can do that at a time. If the 6th one comes in before you process the first one, the connection will be dropped. And then in a loop, we call accept on the connection. So this will wait for a new connection to come in. Once a new connection comes in, we'll have that client socket, that established client socket talking to the other end of the connection. This is my highly performant, 100% standards compliant HTTP parser. If you remember, the first line of a HTTP incoming connection is the verb and then a space and then the path and then a space. So I just split on spaces and then take the second one to get the path, ignoring everything else. So we're going to expand path based on the path that we get in from the directory the file is currently in. So we can just get any file on the file system. This is a static web server. We look to see if the file actually exists, the one that was passed in, and make sure it's actually a file, not a directory or something like that. If it is in fact there in a file, we return the contents. So we look the file contents up off the file system, write out the OK. It's defined in that constant. We send out the content length and the file contents after 2 new lines. This is the else case of the if statement. If we don't find the file and the file doesn't exist, we just write out that not found. It's constant across every request. So similarly, sending out the content length and the not found. Finally, we close the socket, so that way the connection to the client is closed. So this is a 23-line web server that actually works. I'll show you that it actually works. Hopefully, maybe. Maybe not. I can do it this way. I'll just have to look up there and type. Okay, so I put the what? No, that doesn't work. That's not the problem, Nick. Anyway, okay, so anyway, I'm just gonna try and make the font bigger, but I don't know which keys which. So this is that same server that we were looking at a second ago. I just changed it very slightly because this is a different version of Ruby than I was using earlier, but still the same there. And then I also have just a little file here so we can try that just says hello so coded. Okay, so we run the Ruby server. So 127.0.0.1 port. Stupid keyboard is not. That's not it either. There. Okay. Okay, so we're serving connections. We have our file. Yeah, there we go. There's the file that I put it there. We can also do get the actual server itself. Oops. So there's the file itself. So it serves traffic, responds to the correct connections, everything like that. Proof. So, so also just to prove that I'm not making all this up and that this stuff actually does get used, this is inside of Unicorn, which is a really popular Ruby HTTP server. And you can see this is how it actually serves connections. Serves connections in IPv6 mode. IPv4 mode is a little bit different, uses a different library, so it's a little bit more confusing. But you can see here, we call socket.new, AFINet6, and sockstream, so we're doing IPv6 and TCP. Looks exactly the same as what we were just looking at before. We call socket.bind with that sock adder in with the port and the address, just like we were doing before. And then the way that we accept in Unicorn is a little bit different. So when you accept, if you're trying to listen for multiple connections coming in, the accept only listens on one file descriptor. So if you have two and you're listening on one and somebody connects on the other one, you won't see it. So select basically allows you to do the exact same thing but across multiple, and it'll tell you which one the thing came in on. But inside of Unicorn, the code is exactly the same as we just showed, with a lot more error handling around it. So we have this whole stack now, kind of up to the bottom of maybe where Rails lives. A little recap here. We have the kernel at the bottom, dealing with the most fundamental hardware layer, managing the hardware, managing the process itself. We have syscalls that allow us to call into the kernel to do anything working with the hardware. We have file descriptors that allow us to talk about anything that looks like a file, which is most things in Unix. We deal with sockets to talk about the network, talk over the network, and then we do HTTP to drive the web. Kind of get the whole stack from bottom to top. If you're interested in learning more about this, these are some books that I used. These are awesome. This is Linux System Programming by Robert Love, who's a kernel developer. The second edition just came out, so this is really modern, really up to date. It's only Linux, of course, and it basically goes through all of the syscalls, but it doesn't really cover networking. So it's kind of all the other stuff, dealing with syscalls, how they work, and then all of the like fork exec and a bunch of other stuff that it covers. It's really good. For network stuff, Unix network programming, this is the Bible of network programming by Richard Stevens. It's a little bit more dated and it covers everything. It's not just Linux, so Solaris and everything else. And also by Richard Stevens is Advanced Programming in Unix Environment. So this is kind of similar to Linux network programming, but for all of the Unixes, and is very comprehensive. It's a big book. It's an excellent reference. I wouldn't recommend reading the whole thing. So my name is Andy Delcambre. I go by Delcambre on the internet. I work at GitHub, mostly on backend stuff, as you might imagine from this talk. And thanks a lot. That's it.